Okay. Welcome to the final day of the session. And yeah, today is going to be stat session. I would show you some data normalization techniques, and then Madeline would and Philip would take the stat session, and then you can just work on your own data. Once. Oh, I need to. Okay. Yep. Cool. So far we've seen in the last 4 days, what are the techniques you could use to get good data, the good practices, and once you collect your MS2 spectra, how you could convert it to .mzml formats, and then also perform, also MZMine and feature-based molecular networking. And we've also seen for annotation, series, and yeah, like the GNPS. And finally, we've got this feature table. Yeah, the feature table from the MZMine looks like this. You might have already opened it in your Excel file, where you have all these samples in columns, which are your MZML files. And in the rows, you have all the features or the compounds and the corresponding peak area or intensities as given here. And the metadata is something that we create in Excel, but it's better to save it in tab separated format, just information. This is also you would have created to perform feature-based molecular networking. And the first column, as Daniel mentioned, you have to have the column name as the file name, and it is really necessary if you're giving it to GNPS, because for the compatibility, to avoid compatibility issues, they only take in the names if you give it as file name. If you give some other name, then it would not recognize it. So there you have all of your MZML file names as you have in your feature table, and then all the other attributes, which if you want, you could just add it. And one more thing I have not added here is that you could, it is also necessary to have a prefix attribute underscore. This is all these informations are also available in GNPS. They have some rich documentation, and yeah, you just gotta have these attribute underscore prefix to the attribute columns that you add on to. So once you've got this feature table and your metadata, then you could perform data cleanup. Which is like, as I shown here, like some batch correction, blank removal, and imputation, and some of the normalization techniques. I would show them in the coming slides. And once you've got your data kind of cleaned, then you could also perform multivariate and univariate stats and visualize your data, which will be covered in the upcoming session. And disclaimer, all these data normalization and statistics are very data dependent. You have to have a clear idea of what the data you're giving in. And yeah, it should be tailored. There's no, just one perfect way for all the kind of data. And a little recap into the data that you're using. So we are having the plasma and skin samples. Skin samples taken at 3 different locations: upper back, forehead, and forearm. And yeah, all these subjects has been administered with this diphenhydramine drug, and we are monitoring the drug and the drug-related compounds at different time points, with the samples taken at different time points from these plasma and skin samples. And the instructor team, which is for this session and the next session, we will be working on the upper back samples, and the assigned group, you will be working on your forehead and forearm samples. So in the script, you got to change it according to your data. So first, we have to look for, of course, batch effects. When you run your samples in multiple batches, you might encounter within batch effect or between batch effects, which is if you run your samples over a long period of time, there might be some changes in retention time shifts, and also due to some of these instrumental issues, kind of like this gradual contamination of this LC columns, there might be this peak shifts. As Martin already showed in his talk, it would be great if you had your pooled QCs, you could just basically observe their intensity changes. And also one more thing is you've got to randomize your QC samples across your batches. So one another way is also you could use a simple PCA or PCOA plot, which is principal component analysis or principal coordinate analysis. Yeah, along with it, you could also perform PermaNova to assess how much is your batch effect. Is it significant or not? And I'm not also going to go deep into that because Madeline would explain all those things in the multivariate session. But you have a basic idea that when all these points cluster together, they have a little variation, and when they are like spread apart, they have kind of higher analytical variation. And if you have your pooled QC samples, and if they are clustered together, then that means then you have lesser batch effects. And when you have it dispersed apart, yeah, you might have some more batch effect that you need to correct for. And this is like, just to give you an overview, for this data set, they first run all the plasma samples and then the skin samples. They are two different sample matrices. They are randomized within those samples. We did observe some batch effect. Fortunately, it did not affect the question that we was asking, like especially about the diphenhydramine drug. So we didn't touch anything. We didn't perform batch correction. So I'm just wanted to give you an idea that if you observe batch effect, you might need to do it. So then for blank removal, this is where we remove all these blank features or background features. So while measuring your samples, you might have used your solvents as well to extract the samples. So these we also call as blanks, and you could use these blank samples, and practically these blanks are also in all of your samples, right? So we need to remove all these background features from these samples. So here we are just seeing how much of this blank features are contributing to the sample features. And in the script that you guys will work on, there's this cutoff range of 0 to 1, which is like 0 to 100%. And you can define how much amount of blank features I want to remove. You could be either stringent and remove many features, or you could be a little bit like, okay, you can just play around with the numbers. For example, if you put in 0.3, then 0.1, then you are allowing a little bit more features to be there in. But if you're using 0.1, you're being strict and removing kind of as much as features. Yeah, and we have used 0.1 cutoff, and this is the total number of features that were there. And with 0.1 cutoff, we removed 613 features. You could also play around with this number and see how much features you remove. And after blank removal, this is what we observe. I'm just looking at this drug, so blanks doesn't even, this drug is also not in the blank, so it doesn't change anything here. And the second step is imputation, as it's been already discussed as well. The data is super sparse. There are so many zeros in it. So this is for certain applications, mathematical operations like PCA and all, it doesn't deal well with the zeros. So what we do here is that we want to impute these values. So we basically take the minimum value in the feature table, and then between 0 and this minimum value, for each of these missing value, we just randomly impute it in order to also have some variability within the data. But this variability should not be affecting the real variance as well. So we are keeping it below the minimum value in the feature table. And this is what you observe here. So yeah, as you see in the plot as well, the variance is actually between the two different sample types. Of course, they are completely plasma and skin samples. And also after imputing, there is some variance in the second axis, but it's just way less, 2.6, only 2.6% contribution. So yeah. And then after imputing, you could either perform normalization or scaling. It also depends on like different techniques. And both of these methods try to reduce the variations across your samples. So some of the there are so many normalization techniques, but some of the most commonly used ones are the total ion current or TIC normalization. You could also call it a sum normalization. and the second one is probabilistic quotient normalization. More than the algorithm, I just wanted to show you like when to use what, because when you have a deep understanding of your data, then you could choose the appropriate normalization technique as well. For example, TIC is the most simple, computationally inexpensive technique because this is just some normalization. And it is perfect for our data set because we have kind of injected diphenhydramine in all the subjects and the effect size is small. However, if you have significant size effect, whereas you're looking at control group and then for example, diseased versus healthy state, where it's been administered to one group and not in another group, something like that, where the effect size is higher, PQN would be a better choice. So here, after normalization, you could see that, of course, you would find the amount of the drug high in plasma as its blood sample, then in the skin samples, and you could see the normalization effect. And then, yeah, yeah, it's basically just some normalization. You just normalize it, each of these feature values for each sample divided by the total sum of all the intensities that you observed for that particular sample. And yeah, then we can also do scaling. Here, the main idea is that you want to keep all these fluctuations around zero, but instead of the sum or the mean of the metabolite concentrations, yeah, we are just especially we have been using center scaling. We are trying to keep all these variances around the zero. And yeah, like also it is important to know about the normality thing, which I guess Philip would explain. Yeah, pretty much these are the steps we're gonna do, and also the Google Colab script has pretty much all the information. So you could also, so that you guys have enough time to slowly go on your pace. And now I would just go to the Colab. So you could see. So you could just open it from the GitHub page. Ah, okay. Yeah, so if you go to your GitHub page and towards the end, you have this open and collab button, and there you get all these options. And here, just click on the data cleanup. And all these codes are written in R. Yesterday, you guys would have worked with Python, and today all these scripts are written in R. And yeah, you could just practically go with one by one, all the steps. I guess this is the one. Yeah. No, it's a language I don't understand. Ah, it's.
Sorry, man.
I guess, yeah. Okay, I didn't understand. Oh, okay.
Yeah. So let's just save a copy and drive, and they should do that as well.
Okay, so you could all save a copy in the drive and just work on that copied one, just to make sure that we are just working in our own thing and it's not affecting the speed. And I'm not going to walk through all the steps because I guess it's pretty understandable. However, if you find any difficult, we can just walk around and ask you. But just to give you a short idea, you can click on the left-hand side on the this icon, and it already gives you kind of these sections that are in there. So first we install all the libraries, like with install packages, and then we have to call all these install libraries, and we kind of access them for this environment by calling them here with the library function. Yeah, it's already loaded. And then we are retrieving all this data from the GitHub using this URL link. And yeah, you could just click the link for your according group. So, oh, sorry, the metadata. And also the according your metadata. And then you can just have a look at your data. The other thing that you have to change would be here in the subset.
Just zoom in a bit because it's a bit.
Okay.
In the bottom, yeah.
I guess now it's clear to see. And then if you go down, I think you just have to change in two places, like in the sampling location, it is upper back, since you might have to change it to forehead, or forearm. And then you could also play around with the background score values where you have to enter it as the cutoff value, which is in the blank removal step. Yeah, here. So these are the only input values you might be giving. Other than it is just, you can just run through it. But yeah, if you want me to explain, I would explain. But you can also work through it on own. What do you prefer? Do you want me to walk through, or you can just do it on your own pace? Yeah, sure. Yeah. Yeah. Yeah, we should have kind of randomized them, but then yeah, like I think it's
There's the
oh, sorry. It's based on the intensity. We just compare if a particular feature intensity, for example, if that intensity for the feature, it's kind of 10, and then it's also 10 in the sample, maybe that feature could be, if it's also found high in the blank, then probably it's from the blank. So you might remove that feature. So you just, this is where the threshold plays a value. You just set the threshold and yeah. Yeah, yeah. So you're not entirely removing all the features that are present in the blank. And for the ones on the Zoom, the question was if the blank removal was, we are just removing all the features in the blank, or if it's based on the intensity. Okay.
Yeah.
So maybe then I can just walk through. So once you have installed it and called the library, then yeah, this is the URL link of the data from the GitHub. We are just getting the raw data from the GitHub because we already uploaded the data in the GitHub, and you just click it like the play button, and you have the data in the URL. And I've clicked the example set, and you have to pick your group data and then also the metadata. Sorry. Then we are now reading the files from the URL. And the head command gives you like up to the 6. Usually the header command gives shows the first 6 rows of your data. You could also specify how many rows you want. Here we are showing the first 3 rows. And the dim shows the dimensionality. So there are 6,000 some rows and 102 columns. And you could also scroll through your data. And the metadata, as I said before, you should be having the attribute suffix, prefix if you're making your own data set. So this pkda extension is something, and then we are storing it under a new variable name in order to preserve it, preserve the original one. And this pkda extension is something that comes usually when you get the data from MZMine. So we are just doing some little corrections, like changing the column names to keep it the same as your metadata. And then if you have any extra NA columns in your metadata as well as your feature table, you remove it. And then we give row names to this new feature table in a way that, as shown here, you have your feature ID, and then you have your MZ value, then your retention time. And yeah, we have to also give X in the start so that it reads it as a character. So usually it should not start with a numeric value. So just some little details. So once we've changed it, then we would just have the MZML files. Here, we would just pick the MZML files, and we would leave all these extra columns out of the feature table. And same with the metadata. So now the metadata and the feature table has the same file name, so we could just call it that way. But at the same time, you have also an idea of all these features, so we have these row names. And then with the table file, you could, the table function, you could see the different groups in your data. With the sample location, the not applicable belongs to the plasma blood samples, whereas the other 3 different groups you've got. And in the attribute subject, the not applicable is, I guess, the blanks, the 4 blanks that you've got. And then the different volunteers, the subjects, the samples from different ones. Yeah. Then we subset or filter only the upper back and blood samples for me, for my data set, and you could just change it according to your group. So now my metadata would only contain the files from the upper back and plasma samples. And then I pick the corresponding files from the feature table. And so now I have 88 files in total. And you should be having 88 files in total as well. So this is to see if the column names are the same. Here we saw, and it says true. So we have the same files. If it says false, then you could run the next line and see which column names are different, and then probably go correct it. And we just are checking, like we started with 102 columns, and then we subsetted it with this new FT. We only have 88 columns, which are the 88 files. And in metadata, we have that in rows. So we have like 88 files and then 6 attribute or 6 columns information. So now in the first step of data cleanup, we first transpose it. As I said, here, this is in columns and here this is in rows. So we just transpose it so that both samples in both the tables, the samples are in rows. So as you can see, 88 rows now and 6,000 some columns, which are just your features. And yeah, this is where you perform blank removal. The first step is to split the data as blanks and then the samples. So first we split for the blanks, the metadata for the blanks, and then from using the metadata, we get the corresponding files from the feature table and we call it under blanks. So for blanks, I give both plasma blank and skin blank. And you don't have to change this one. And also looking at the dimension, there are we have 4 blanks and it shows 4. And for the next one, I'm just using the sample type attributes. So you don't have to change anything here as well. We pick both the plasma and skin samples, which is our samples. And then here you could just pick your cutoff. I'm just running 0.1 as of now. And as you can see, you kind of, for every feature, you're getting an average value. So at the end, you have kind of just 2 column, let's say, for every feature, you have 2 values, 1 average value from the blanks and 1 average value from the samples. And then you basically take a ratio of it. And then you're seeing if it is greater than the cutoff that you provided. If it's greater than the cutoff, then we call it true or 1. And if it is lesser than the cutoff, then it would go under 0. So we are just gonna, retain the one which are lesser than the cutoff. The ones which are greater than the cutoff, we're gonna kick them out. So these 613 were greater than the cutoff provided, which is 0.1. We could just also play around. And you see, you have, I think I said wrong, we have 400 and with 0.8, when you increase the cutoff, you see the background features are being lessened. I'll just bring it back to. Then we only so this is just to see which features are, and then we subset those features from the samples. We are not technically changing anything in the feature table. We are just trying to find out which features could be from the blanks. Yeah, first we see kind of like a frequency plot where you see the different distribution, like a histogram. There are so many zeros in here. And yeah, from 1 to 1,000, this is the range, and in the range of, tens, and in the hundreds, you have these many values. This is just a normal histogram. And then for each of this zero value, sorry, I said it wrong before, I guess, like between 1 and the minimum value, we kind of pick a random value and then impute each value, each missing value with it. And the set seed is there to kind of get the same values. If you don't set seed and perform this randomization, then for every time you would have different values being put there. So with set seed, every time you repeat it, you would generate the same values. We choose a number between here, we choose a number between 1 and the minimum value in the data set. Sorry, the minimum, yeah. And I guess here you would see that the minimum value, which is not the 0, here is 6. So you would practically, for all these, you would see something like, yeah, I guess this was, I'm just going back to the blank removal table. Yeah, you see here, there are like so many zeros, but then if you go to the imputation value now, it's been imputed. You see these 3.6, 2.2, all these values. Since these are like really low values, the idea is that it would not affect the actual variance so much. I think I can run something. Could not find the function. Oh. So I just rerun it. I'm just quickly wrapping it up because we have also to go to the next session. And yeah, for scaling, we are again taking in the imputed data. I just ran the normalization. I'm not writing it as CSV files. If you can also write it as CSV files.
They have a question just where like the everything that's on output where it ends up, if you can show just where the CSV files and so on.
Sure. So here, if you on your left side, if you click on this file button, you would see the files that you have saved. For example, I just ran the CSV file output, and from here you could just download it. And yeah, then you basically just have it downloaded locally in your, which you can find in your downloads. And that's all I wanted to say. If you still have some questions, I would be happy to come around and help. But before then, I also wanted to show 2 more slides. Can everyone see Zoom? Okay. Yeah. No? I Cool. Thank you. So just some final words. So last summer school, we kind of followed the same sort of we also showed everyone the data cleanup and the univariate and multivariate stats. And with that, we also decided to write an article about it. And so many of the people from the VMOL group, virtual multiomics lab, contributed to it, and also so many people who are here. And yeah, so we are still writing this article, Hitchhiker's Guide to Statistical Analysis of Feature-Based Molecular Networking. I just put one picture here, but then there are so many people involved in it. We basically show, it's kind of a tutorial come review article, you could say. And we practically show everyone how they can, once they get the feature table, and which is, yeah, from the MZ-Mine, we particularly focus on MZ-Mine, and what you can do with your data. So we show it in a step-by-step format. We have it in R format and Python, and we also try to show in Chime2 platform. And Axel also helped us to make a cool app out of it. And it's still in preparation, so please don't go and break it. And in Streamlit version. And yeah, and I also have some stickers for the VMOL thing, and you could also be a part of it, and feel free to take it. And then we'll see you soon there. The final slide is thanks to everyone for this amazing summer school. Yeah, thanks everybody.